This is simple harmonic motion, problem 1996, and it is number 2. This one's 15 points. You've got a spring just kind of hanging off of a spring stand. We've done this lab. We did it both ways, so you shouldn't have a lot of trouble with this one. They want you to find out what the spring constant it is. So instead of going through and writing all this out, I'm just going to bring up the key so you can see that what we did in class is pretty much the same thing. In order to get full credit, you'll notice that it says a solution must completely follow through one method. So if you pick a method, just stick to that method. Don't try to combine the two. That doesn't really work very well. At this point, we're going to look at the two methods. This is the one where you use F is equal to negative kx, and this one is where you use the period of a spring is equal to 2 pi times the square root of m over k. So in both of these, for method 1, you need something to measure distance, and you need a mass or a force probe so that you can continue to add those masses. And remember, this force is really just mg. It's the same thing. And at this point, for method 1, you would hang the mass from the bottom of the spring, you would measure the extension, remember that's your x, or you can pull it down with a force probe. So we did that, and remember when we did that, we had force, and they did time in the lab originally, so remember we had to switch that to distance, and you ended up with a graph that looked like that. And then the slope of this line was the slope of this line was our k value. On method 2, we had a stopwatch and a calibrated mass. You would set it into SHM, simple harmonic motion, and measure the period. From that, you could then plug in the mass that you knew and plug in the period, and 2 pi are just constants, so then you could solve for k. So either method is fine, but you have to stick with one method. So if you start with f equals negative kx method, just finish with it. Don't even try to do the other one. If you try to mix them up, they won't give you all the points. If you just do that much, that's 4 points altogether. So that's kind of nice. For the next part, you'll see that they want us to assume that the spring constant is determined to be 500 newtons per meter. You have a 2 kilogram mass, it's attached to the lower end of the spring from rest, and they pull it down and it goes up and down. So we want to know what is the frequency of this thing. Obviously, we can't use this equation because it doesn't have anything to do with frequency or period. So the equation we need to use is the period of a spring is equal to 2 pi times the square root of m over k. But our problem is we don't want period. We want frequency. So there's two ways to do this. We can either plug everything into the equation, find the period, and then we know that the period is equal to 1 over f. So f could be equal to 1 over the period. You can also go through, and one thing that they did in their analysis of this was they went ahead and just plugged everything into the equation and just took the reciprocal. So they do 1 over 2 pi times the square root of k over m. It's the same thing. It's just that now we're looking for frequency. They then plugged everything in, so we have 1 over 2 pi times the square root of, and then we have to use the k value, which is 500 newtons per meter, and then our mass is 2 kilograms. Do make sure that that's in kilograms. When you're done, your frequency should be 2.5 hertz, and that would give you all three of the points for this one. Your first point comes in when you substitute everything in, the correct number answer, and they actually do give you a point for the unit. You either have to have hertz, 1 over a second, or you need to have seconds negative 1. Any of those units would work out. You could also say cycles per second. So any way that you do it is fine as long as you have one of those 4 units that I just showed you. Finally, last part says, suppose the spring is now used in a spring scale. It's limited to a maximum value of 25 newtons, but we have something that has a mass greater than 25. We need to figure out a way of doing this without breaking the scale. So we'll go back to the key again, because I think the key does a better job than what I can of going through and kind of showing you what the correct answer would be. Um, they want us to go through, and there's a lot of different ways to do this, but you just really need an apparatus that will measure some weight that greater than 25. So you have to have a lever or a pulley system or an inclined plane. The apparatus needs to measure over an infinite range or a correct indication of limited range of the apparatus. So for example, what you could do is have an inclined plane where you can actually stretch that spring along the inclined plane. So you'd have your spring right here, and then you would have your mass, and that mass can now be greater than 25 newtons, because remember, we're not looking at mg on this one. We're really looking at the force down the hill, which is FD. So the smaller the angle, you could have it work a little bit better, but you might have to make this thing really long in order to do this. So you might have the spring actually up on top, connected to a post, and then there's a string that would come down to the mass. Um, or you'd put the mass here and then let it stretch. So that's got to be pretty long. Um, so that's 2 points for just the incline or the pulley system or a lever, and then 1 point for the oh shoot yeah, for the limited range. So how to do that. So you've got to kind of look for it. For the very last part of this problem, for section double I, it says explain how you would make the determination. At this point, they also tell you here that you have to have a diagram. So the diagram that I drew would be fine. You might want to label it a little bit better than what I did, and that will give you the correct number of points. For this part, just kind of explaining for correctly identifying all the quantities that you need to measure, explaining how to determine the weight from the measured quantities, so you'd have to show the triangle here, and for the practicality of the measurement. So whether equipment is commonly available, so you wouldn't have anything that's frictionless or massless, whether the object remains intact. So this is one that I'd probably, if I saw I had to go through all this stuff for 3 points, I would try to get down just a little bit to try to get a point or two, and then just be done with it. Other problems could be a little bit easier to tackle.